All right, let's jump right in. We're talking about a technology that is set to completely change our world, from medicine to creating new materials, all the way to the very nature of information itself. This is quantum computing, and today we're going to unpack what it's all about and why it's such a massive, massive leap forward. Just think about that for a second. Let that sink in. This isn't just about making our computers a little bit faster. No. This is about creating a whole new way of computing, one that plays by the weird, wonderful, and frankly mind-bending rules of the quantum world.
So where do we even begin? Well, it all starts with the most basic, fundamental difference between the computer on your desk and a quantum computer. It all boils down to its most basic building block of information.
And here is where the magic really happens. See, the device you're watching this on right now thinks in bits. They're like simple light switches. They can be on or they can be off, a 1 or a 0. That's it. But a quantum bit or a qubit, well, it can be a 0, it can be a 1, and incredibly, it can be both at the exact same time. And that right there, that ability to exist in multiple states at once, that's the secret sauce.
Now there's a name for this, of course: superposition. The easiest way to wrap your head around it is to picture a spinning coin. While it's spinning in the air, is it heads or tails? Well, it's neither. It's in a state of both possibilities at once. It's not until it hits the table, until you actually measure it, that it's forced to pick a side. A qubit is just like that spinning coin, living in this world of pure possibility, right up until the moment you look at it.
Okay, so we've got superposition. But believe me, it gets even weirder from here. And it's by leaning into these totally bizarre rules of physics that quantum computing gets all its incredible power.
But here's the catch. You can't just sneak a peek at a qubit while it's in superposition. The moment you try to measure it, that spinning coin hits the table. The qubit is forced to choose, instantly collapsing into a definite 0 or 1. And just like that, all of that rich quantum potential, poof, it's gone. It just becomes a plain old classical bit. So the very act of looking at it changes it. Wild, right?
All right, if you thought that was weird, buckle up. Because it turns out you can link two of these qubits together in this really special way called entanglement. This creates a connection so bizarre that even Albert Einstein was freaked out by it. He famously called it spooky action at a distance.
So imagine this. We entangle two qubits, so now they're basically one single system, right? Now we take one and leave it here on Earth, and we put the other one on our rocket and send it all the way to the other side of the galaxy. The second, not a nanosecond later, the instant you measure the Earth qubit and it decides to be a 0, you know for a fact that the one galaxies away has also become a 0. And get this, no signal traveled between them. Their fates are just linked. So this spooky connection has a couple of really key features. First, it's a private club. If two qubits are fully entangled, nobody else can get in on that connection. It's totally exclusive. That's monogamy. And second, like we just saw, their coordination is perfect and instantaneous. You put those two things together, and what do you get? Well, you get the recipe for things like completely, truly unhackable communication.
And this all feeds into another really cool, kind of counterintuitive rule, the no cloning theorem. Basically, you can't just hit Control-C, Control-V on an unknown quantum state. It's impossible. Now that might sound like a limitation, but it's actually an incredible security feature. If an eavesdropper tries to copy your quantum data, the very act of trying to observe it actually changes it, so you'd know immediately that someone was snooping.
Okay, so superposition, entanglement. This stuff is amazing, right? So the big question is, why don't we have quantum laptops? Well, the short answer is, building these things is incredibly hard. Like one of the hardest engineering problems humanity has ever decided to tackle.
And the main villain in this whole story has a name: decoherence. You see, qubits are unbelievably sensitive. The tiniest little vibration, a stray bit of heat, any random noise from the outside world, and poof, the qubit loses its quantum magic and just collapses. So the whole game is trying to shield these fragile qubits from, well, pretty much the entire universe.
So how on earth do you even start to build one of these things? Well, thankfully, there's a roadmap of sorts. A physicist named David DiVincenzo came up with what's basically a 7-point checklist. You can think of it as the 7 commandments for building a real working quantum computer, and labs all over the globe are in a frantic race to check off every single box. And let me tell you, this list is no joke. You need a big system of stable qubits, you need to be able to reliably reset them all to 0,
You have to fight off that decoherence long enough to actually do a calculation, and you need a universal set of operations, or quantum gates, to actually run your programs. And that's just the first 5 points to get a single computer working. The last 2 are even bigger. They're about networking these machines, turning quantum data into something that can be transmitted to build a future quantum internet.
What's so fascinating is that there isn't just one way to build a qubit. It's a full-on race with different teams taking completely different approaches. You've got giants like Google and IBM using these tiny superconducting circuits that have to be kept colder than deep space. Others are using quantum dots, which are basically man-made atoms. And then you have the really wild out there ideas, like trying to braid the paths of exotic particles to create naturally error-proof qubits. It's just an incredible scientific adventure.
Okay, so we've talked about the physics, which is weird, and the engineering, which is, wow, hard. So let's get to the payoff. Why are we doing all this? What's the point?
Because the potential applications are, and I'm not exaggerating here, world-changing. Think about it. Our natural world runs on quantum mechanics, so if you want to simulate a new molecule for a life-saving drug or a new material for a super-efficient battery, a quantum computer is the perfect tool. We could literally design these things atom by atom. Not to mention creating those unhackable communication networks and financial models that can finally grasp the true complexity of our economy. And you can see how it all circles back, right? That spooky entanglement we talked about, that's the backbone of a future quantum internet. That weird no cloning rule, that's the principle that makes perfectly secure communication possible. Every single one of these strange quantum features isn't just a scientific curiosity, it's a superpower waiting to be unlocked.
And all of this work leads to the Holy Grail, the term you hear thrown around all the time, quantum advantage. And let's be really clear what this means. This isn't just about being a little bit faster. This is about reaching the point where a quantum computer can solve a meaningful problem that the biggest supercomputer on Earth couldn't solve if you gave it 1 billion years. It's not about doing things faster, it's about doing the impossible.
And that leaves us with the ultimate question. Once we finally achieve this, once we unlock this new era of computation, what problems will we solve? Could we design a catalyst that pulls carbon right out of our atmosphere? Could we finally unravel the mysteries of consciousness by simulating the brain? The possibilities, they're truly as vast and limitless as the quantum realm itself.